I'm going to assert in the interest of time that writing correct code is difficult. If you don't agree with me on that, just pretend, okay? Now, to make sure that something does work, there are a whole bunch of things you can go through to make that happen. So the first thing is you need to choose the right tools, which means you use the right operating system, you use the right language, you adapt all those to your workflow, to your team and your company. And then the next step is to decide whether verification is something you can pay for. Is it worth proving that your CRUD web app works? Probably not. In fact, I've seen very few cases where actual formal verification is worth it, but maybe it is, so check it out for your team. And then the next step we usually get to is testing, and that's what I'm going to be talking about today. So I noticed that there are problems with testing, and in fact, I'm looking at a unit test right here, and I noticed that there are at least two problems. The first I call the coverage problem, and the second I call the price problem. The coverage problem states that you have to write a lot of tests in order to have any confidence that your thing works. And there is actually no amount of testing that will make you extremely confident to the point where there is nothing else you could write to be more confident. And the second problem with testing is called the price problem, where writing tests costs time, money, it's tedious, people don't like to do it, you have to press a lot of buttons. It's not fun, right? There may be people who are here who like to write tests, I do, but I noticed that a lot of people don't. To give you a bit of a statistic, there was a Stack Overflow enquete where the results showed that 70% of all programmers have never written a test, and 40% of all programmers have never seen a test. I'm not kidding. So this was shocking to me too, but even if the level was 10%, it would be too much in my opinion. Because in my opinion, testing should be a fundamental part of building your application as opposed to something after the fact. Anyway, I have to go on. So this is where we introduce property testing. I'm going to give an overview of all of property testing in Haskell. Most of what I say is applicable in other languages. A lot of what I say I've seen in other languages and has already been implemented. But I'm just going to give you an overview in Haskell because that's where we can go the furthest even into research. So if you think about a unit test as a block of code and you run it and then either it crashes or it doesn't, that's a, let's say, a simplified view of what a test is. And then you could say that an assertion is just a fancy way of making your code crash. Then you can say that a property test is just some unit test with an argument such that you can get the argument from somewhere, and what you're asserting is that your code should never crash for whichever argument you pass in. So then the arguments that you can pass in can either be randomized or they can be exhaustive, so all of them. And here's an example of one such test, so one such property test. So what you see here is a test that is a function from string to bool that either crashes because it's not equal or it doesn't crash because it is equal. It's a bit annoying that this goes to bool instead of IO unit, but you can imagine what this does. So the test here asserts that if you reverse a string twice, it's the same string as you started with. This is almost enough code to actually have a property test running. So to get the input so this is all the introduction I will give you to property tests, because I have to go on with the actual overview of how we implement this in Haskell. And to do that, I have to pick apart how we pass in the arguments to the property tests. I chose to use randomized property testing, not exhaustive property testing, which means that we use randomness to generate the inputs to the property test. In QuickCheck, which is the first thing I show, a generator of A's takes a seed to make deterministic randomness possible, and a size, which guides the size of the value, takes those both together to generate A's. And then those are passed into the property tests. And then the other thing that's important next to the generators is shrinking, which is what happens when a property fails to assert that a certain value gives you a correct answer. So that means if your test fails with a certain value, then we're going to try to shrink the value, because most likely the value is very big, complicated, and random, to something more manageable and human-sized, which would make it easier to debug. So here's an example with shrinking turned off. Here's a property test that checks that if you uppercase all characters in a string, then all the characters become uppercase. Who thinks that this should work? I mean, I already have the test failure, but I certainly thought that this would be true. So it turns out it doesn't, and here's a nice counterexample. Can you see why? Probably not, because this is a really long, complicated string that doesn't tell you at all why this is not uppercase. They certainly look uppercase to me. I mean the uppercase version. So if you try to shrink this, that means you're going to try to find a smaller version that still fails the test. If there's a smaller version that doesn't fail the test, we just ignore it. So here is the same test, but with shrinking turned on again. And what you see is that if you uppercase the character 1, it stays 1, which is not uppercase, so the property fails to pass. So here are the libraries that I'm going to be showing you, or telling you about rather. I'm only going to show you 3 of them. There's QuickCheck, which is the original from a while ago. Then there's Hedgehog, which is rather new and has very fancy output. Then there's validity-based testing, which is even newer, which tries to solve a bunch of problems. Then there's leanspec, which is something, I don't want to call it a toy, but it doesn't seem to be something that someone uses in production. It's just an alternative implementation. There is smallcheck, which is exhaustive property testing. Then now come the next pieces, which are more research-based. There's Quickspec, which allows you to pass in your code and output the properties of your code. Then there's speculate, which does something similar but different concept. Then there's Easyspec, which does the same thing except easier. Then there's extrapolate, and it is it tries to, I think if I remember correctly, it takes a unit test as input and produces a property test that would have the same effect. And then there's fitspec, which, given some property tests and your code, will try to change your code and see if the tests now fail, and if they don't fail, then you don't have enough tests. So this, actually the output of that is great, because it has it is something like 13 mutants survived in your zombies. Like, it's really cool to see the output, but anyway. Good, so this is the overview of the libraries that I'm going to be talking about. So in QuickCheck, the way we do the generating is that there is a type class called arbitrary, which has 2 functions. The first is called arbitrary, which is a generator for such a thing. And the second is shrink, which is the shrinking function that will be used if a property test fails to assert that a certain property holds. And here's an example of how you write a property test in QuickCheck. You say you give a function that can be tested to QuickCheck, where the argument can be generated, and then the output is something akin to a unit test. So here it's the same property test. If you reverse a list twice, it's the same as reversing it once. Right, so this generated 100 inputs, 100 strings, and it seems to pass. The fun thing you can do with property testing is something called property combinators, which is where you pass something into a function and get a property out. So for example, if I have this custom operator that you don't need to know because it doesn't exist, you can make a property combinator that says, for any function that returns a Boolean with 2 arguments, I can now check if it's reflexive or not. And then I can check whether it's associative or whatever else. So you can pass in a function to a combinator and not get a property out. The problem with this approach in QuickCheck is that this only really works if all of the values of your type make sense. So for example, this property of reflexivity for equals does not hold for rational, for example, because rationals need to be normalized in order to make sense. So that's one of the problems with the QuickCheck approach to doing these combinators. There are some other problems. So there are ways to fix this, but I'll get to that in a moment. Then the real problem with arbitrary is that there are no laws for it. So if you were to try to implement a generator for rational, for example, which is just something divided by something else, the question is, do you want to generate 0 divided by 0 or not? Do you want to generate 1 divided by 0? Do you want to generate 5 divided by -0? And if you do want to generate that, do you want to generate -5 divided by 1? Like, these are all questions that the arbitrary type class and its non-existent laws do not give you any answer to. So if you never generate the unnormalized values, so that's something like 2 divided by 2, then you never test certain edge cases. If you do generate them, then standard functions like equality break. And there was another option, which I forgot about, and is also not in my slides, it seems. So the way QuickCheck tries to solve this is by using new types to to guide the generation of values. So you have an instance for arbitrary rationals, but you also have you could have a new type called normalized, such that the arbitrary instance for normalized rationals only generates normalized rationals. The problem is that, is there an echo? Okay. The problem with that is that all your property combinators are now super verbose. So also not so great. So you can't compose these. So if you want non-normalized and also not a number and also not infinite numbers, then you need like 3 levels of new types. Becomes really ugly really quickly. So the real problem is that writing these generators and these shrinking functions is really expensive. To write your generators, there is no default implementation, so you have to write it yourself, and the explanation that I found on their issue tracker is right there. So there are ways to do it, but it's not built in. There is no default implementation for arbitrary at all, so you have to write your own generator. There is no default shrinking at all, so you have to write your own shrinking function. In fact, the default shrinking method does exist, but it doesn't shrink. So you still have to write that yourself. Now, I'll get to that in a moment. That's one of the reasons why Hedgehog started existing. The other question with QuickCheck is, where do you put your arbitrary instance? If you put your arbitrary instance next to your data type, then your library has to depend on QuickCheck, which is not something you'd like in production. If you put them in your test suite, then you can't import them from another package because you can only import from libraries. If you put them in QuickCheck instances, then you have to depend on QuickCheck instances, which also contains dependencies that your library may not have. So that's also not ideal. Then there's another option, which is to have a separate library with only your generators itself, but then you have to maintain extra packages. So there's really no nice way to do this at all. Like, I haven't found a solution to this either. And then there's Hedgehog, which is a separate library which uses different generators, different shrinking, etc., etc. It's a bit more verbose, so this is the same example of reversing a list twice and then checking that it's equal to the original list. But now you have to have 3 imports. You have to write your own generator with list, linear, range, something, something, and your own property, put it in the right place. This is a bit more tedious. So the Hedgehog attributes, let's say, is that they have value level generators. So there's no more type class. You have to write every generator yourself, and you can only compose them via other value level generators. There is shrinking built in, so you don't have to write any shrinking function per se in Hedgehog, and it does that with some very fancy magic that I don't fully understand yet. In essence, it generates the shrinking options while also generating the values in some sort of tree I don't understand. Anyway, so there is a way to do shrinking in Hedgehog. It does it automatically via some mechanism that the implementators understand, but I don't. The generators are also more general because you can have arbitrary effects in between the generation of values, which you may consider good, you may consider a bit less good, but this is the way it happens. There are some problems with Hedgehog as well. Hedgehog uses this built-in shrinking. It's automatic, so you don't have to write it, but it's also non-ideal. So here we have a generator for a tuple of characters, and let's say if it generated BB, and I say I only want the tuples where the value is equal, then it's going to have a lot of duplicate shrinking options, for example. QuickCheck also does this wrong because it just has no shrinking options, and then the last one I'm going to show you later does this correctly, albeit a bit slower, and gives you exactly one shrinking option, which is the one you're looking for. The reason why you want no duplicate shrinking options is because your entire test will be rerun with this shrinking option, and if your test involves calling a database, checking the results, setting up a Kafka cluster, you don't want to happen this 3 times for this. Don't want this to happen 3 times for the same value. All right, so that's shrinking in Hedgehog. The other problem with Hedgehog is that there is even more cost to writing the generators because you have to write all of them yourself. You don't get any help from a type class. You can write property combinators in Hedgehog, but you have to pass in the generator that you want to use everywhere. You can't use type class constraints, which means that if you want like multi-level combinators where you say this is a partial ordering, where you want to say if something is a partial ordering if it's associative, reflexive, and something else I forgot. Yeah, doesn't matter. Then you can do that, but you have to string the generators around. Now, that's Hedgehog. Now there's the third option. I have 15 minutes left. Great. The third option is called validity-based testing. That's the last one I'm going to discuss. The other ones are more like research. And I'm going to show you first what I want to have happen. I used to give this presentation backwards where I just build up to the solution. Now I'm going to give you the solution first and then make you go, wow, and then tell you how to do it. So suppose I have some data type and I have some function that does something with this data type. Now I want something almost non-existent that tells me whether this is going to work or not. In particular, I have some invariance in my data type. So I say, for example, there must not be any white space in the name of the tag, and there must not be any new lines in the value of the tag. So I want to write something cheap, which means short, less typing, or easy to read at least, and have it just work. So here's what you can do. There's 4 lines for the generators. 1 line of that is explaining what the validity constraints mean in terms of code. And then you have your single line test suite that does all the checking for you. It generates inputs for you. It runs them to the function and then checks if the outputs still are valid. So this is one of the options. Another example is I have some JSON instances and I want to make sure that they work. I have run into many bugs in production before I used this, where the parse JSON instance was just not the opposite of the to-JSON instance. So I have my JSON instances, I have my data type, and now I want to write something short that makes sure that these make sense. So here it is. You write your 3 lines to make sure that you can generate this. You get your generators for free. You get your shrinking for free. They are all correct. And then you can say, figure out whether JSON is valid or not with my type. And it will generate you the test suite for the JSON instances for that type. Then there's one more example with the functor applicative monad laws. It's not really that interesting because you don't actually write a lot of functors that you can generate. Then there's something similar with lenses. So you can now also test all the lens laws with a single line. And again, you get your shrinking for free, you get your generators for free. So for cheap testing, I want to at least solve the coverage problem with tests. So instead of writing 2 unit tests, I'll write 1 property test and have a lot more effect. So that should at least probabilistically solve the coverage problem that unit tests have. The problem is then that the cost problem is exacerbated in the sense that you now have to write property tests instead of unit tests, which means that you have to think about your code in a much more general way, which is a bit annoying. And of course, you have to write the generators and such. So at least that part is more difficult, but I try to mitigate that a bit by giving you the generators for free, so you never have to write your own generators again if you don't want to. You get your shrinking for free because of the validity constraints. I can talk about that for hours after the talk, but this is too short. And you get cheaper properties because there are a whole bunch of property combinators and test suite combinators already implemented for you, and I rarely need any one of them that is not already in this library. So I already told you this. Oh, right. So to get you the free generators, I should have some way of implementing a generator based on the structure of the type, and you can do that using generic programming. Essentially what happens is if you have a product type, generate both of the parts. If you have a sum type, generate either of the parts, and that's essentially it. So you get your generators for free with the condition that means that all of the values that are generated are completely unchecked for any validity constraints. So this is called gen unchecked. Gen unchecked, so you can get free things if you want to generate them, but they will not maintain any invariant. Okay, so now what if you do have invariance, for example, in a new type like this, which says that the integer inside the constructor is a prime number. What you can now do, what you could do, was you write down what that means in terms of a Boolean predicate, and then you can see 6 is not prime, and then this list of primes is not valid, and you have no idea why, because there is some non-prime in the list. So this is actually a bit more complicated than just a Boolean predicate. In fact, you have to explain why something is valid, and then you get your Boolean predicate as well. And here you can now see, in this list of supposed primes, there is one that isn't prime, which means that the list is invalid, and it tells you exactly where the problem is. At index 3 in the list, there is something that's not a prime because 6 is not a prime. Good, so given the unchecked generation and the validity constraints, I now assert that I can give you a valid generator for any type. that there it is. So you generate unchecked values and check whether they're valid, and if they are, that's fine. If they aren't, try again. That's what happens here. To get the shrinking for free, you just shrink arbitrary unchecked values and filter out the ones that are valid. And now you have a correct shrinking function and a correct generator for free. By the way, this validity implementation of validate is also generated for you for free if your type is correct by construction, that meaning that that the thing is valid if all the subparts are valid. So in practice, you usually have to write only 3 lines of code to get your free generators. And they're copy-pastable. So then, to get the cheap properties that I promised, there are a whole bunch of property combinators. Here are some examples. Because of this more general framework that we now have with the validity constraints, you can now say, here's a function, it returns a maybe, and whenever you pass in an invalid value, it will return a nothing. And so that's one of the options. Another one is succeeds on valid, which means that if you pass in a valid value, it will never return nothing. And there are a whole bunch of these. I counted as something over 100. There are also more, let's say, useful ones. No, not useful, fancier ones, where you can say, for example, this function is associative, or these two functions are essentially the same, or these two functions are inverses if they both succeed, or something like that. These have all been implemented already. I use them on a daily basis in production everywhere I go. You can go even further, because if you have an ordering instance, for example, and you want to make sure that it works, there are about 14 properties, so about 1,400 tests that run with a single line of code to make sure that this actually works. In fact, you can pass in a type via type applications and some fancy magic that you don't need to know about, and then get this as the output. So I say ordering needs to make sense for integers, and it goes, okay, here are the 14 property tests to make sure that's actually the case. If you write your instance wrong, you will now know about it. You can do the same thing for higher kind of types, so you can do the same thing for a functor. You don't really do this a lot, so it's not really interesting. Same thing for JSON values. Ta-da. If you pass in a single line JSON spec with your type, it will make sure that when you encode a value, it never crashes. When you decode a value, it's the same as it gets you back what you encoded. The same thing for lenses, which will test the lens loss for you. Here is the sum total cost of what you need to do. You write your type, you derive generic so that it can do the generic programming thing. You say that there must be an instance for gen unchecked. The generators are generated for you using generic programming. The validity instance, you have to declare that it exists, but it is derived for you using generic programming. And you say that there is a gen valid instance. The implementation is via the default instance. So all of the generators for free, all of the shrinking for free, and the shrinking is correct for the cost of 3 lines of your typing. And these are copy-pastable. So there are also a bunch of companion libraries. So I showed you some of the specs for the internal values in the base library, but there are a bunch of others. So if you have a binary serialization, you can do the same thing. If you have a hash function that needs to make sense, you can test that now. That's the end of the validity-based testing. I have 5 minutes left, so that gives me time for questions. I probably skipped over some things, so if something is unclear, now tell me and I will go over it separately. Thank you.